Okay, before we get started diving into the fun and adventurous world of more math, I want to give you, talked a little bit about what our schedule is going to be like for the next 2 weeks. So, you may know this, but Tuesday is a wellness day. So we will not have class on Tuesday. Typically in this class, your assignments are due on Tuesday. You will not have assignments due on Tuesday. Everything that would be due on Tuesday is actually going to be due on Thursday. Okay? Today's going to be our last day of talking about first order systems. Next Thursday, we will briefly discuss second order systems. Just because we're close by, so why not? Then we will do a review of the class, and then I'm going to give you a test. It won't be on Thursday. I'm going to give you it's going to be a take-home test. I'll actually post it on Canvas. Test format's going to be 20 questions, 100 points. Every question will be worth 5 points apiece. We will cover everything that we have talked about in this class from the beginning of the course up to first order systems. So that will include resistance, capacitance, inductance, definitions, and then talking about what we're talking about now. Because I'm giving you a test and because I'm giving you a test outside of class, we will not have class on the following Tuesday either. So for the next 2 weeks, I will only see you on Thursdays. When you get back, after hopefully having taken your test, we will start working on Project 1. For Project 1, you will need your Raspberry Pi. So, two weeks from now, bring your Raspberry Pi. Okay, any questions about that? So next week, I don't see you Tuesday. Your homework's due Thursday. I give you a test on Thursday. It'll be due probably the following Thursday. And then I give you Project 1. Okay. No. We'll assume that that makes sense. All right. So far, we have been talking about first order RC systems. And the reason why they're called first order systems is because it involves one single derivative. So what we're going to mention today is what happens when you have a discharge circuit. So here, if we have this system right here, node 1, node 2, VS, R, and C. When the switch is flipped, meaning it's on, how much voltage is in the capacitor? Well, to figure that out, when the switch is flipped, how many loops do we have? We have 2 loops. This inner loop, and we have the outer loop, okay? So, when the switch is on, well, and then we have this third loop, but we're gonna ignore it for now, because it's just redundant. If we do KVL for, let's make this loop 1, and we'll make this be loop 2. For loop 1, what is the KVL equation? this is 1.
Yes.
Yep. That's it. Pretty simple. What about loop 2? Way to stand up and say something in front of class. Nice work. What's that? I know, right? Real stand-up guy while sitting down. What is the KCL equation for loop 2? Yep. So you'll notice these components are all in parallel. They're all going to have the same voltage. Okay? Unlike what we saw in our last system, when the switch is flipped here, the capacitor charges instantly. It's just like what we were dealing with last week with our system where we have a capacitor and a voltage source. It's very straightforward that way. So looking at this and saying, okay, Vs equals Vc1, there is no charge up time. The resistance slows the current flow to the capacitor, but here what's going to happen is, because we are directly connecting a loop where the battery is connected to the capacitor, that connects directly back to the battery, this is going to charge instantly. For a brief moment in time, you'll have a near infinite current flowing out of the battery and going into the capacitor. Okay? So that's while the switch is on. What happens when the switch turns off? Does the system just stay as it is? Why not? They are in their own loop, yes. I mean, yeah, I was hoping to tell everybody that, but you're not supposed to get right. But yeah, he's right. So when the switch is off, the system changes. Okay, when the switch is on, Vs is equal to Vr1. What that means is that there has to be a current flowing through this resistance. There has to be. Because you can't have a voltage across the resistor without current flowing through the resistor. Okay? Well, that poses a problem because as soon as you turn off the switch, these two components are still in parallel. They just are not, they're no longer connected to the battery. So what you have here is a brand new set of KCL equations. Okay? So switch off. Here, now you only have one loop, and that one loop is this one right here. Both of them still have a voltage. They have to, because there's a voltage across the capacitor. It isn't just like excess charges on the capacitor like, meh, just disappear. They don't go anywhere. The only way they can go is for the excess charges that are located here to travel backwards through the circuit, go through this resistor, come up, and fill where there are electron holes on the other side of the capacitor. That's what has to happen. Now, ironically, current flows through the resistor the same way. Always flows downward. But as soon as this switch turns off, current flows out of the capacitor the opposite direction. This is storing charges. And then Jacob used the correct word. This becomes a discharge circuit, where this capacitor is losing energy, causing electrons to flow backwards out of it, go through the resistance, and then come to the other side of the capacitor. Now when we flip off this switch, no electrons are going to go into the negative terminal of the battery. It's because it requires a complete loop for a battery to both lose and take up charges. So for KVL1, what you have is VC1 is equal to VR1, which this equation was true before. It's just now the only equation we have. So what happens in this discharge circuit? Okay. Well, here the resistance, because the current coming out of the capacitor has to go through the resistor, resistors do not allow for infinite current. Do you know why? Anybody want to take a guess? Huh? It would be, yes, because you can have an infinite amount of current. On a short circuit, you can't have an infinite amount of current because you have no resistance. Why is it that you can't have an infinite amount of current when you have a resistance? So yes, you're right, but you're answering a different question than the one I asked. Well, yes, it does slow it down, which means you won't have the infinite value. What I'm trying to get at is this. Our old good friend, Ohm's law. If you have an infinite amount of current traveling through a resistor, what's the voltage on that resistor? It's infinite. Which means all of a sudden, now, if this were to discharge immediately, you would have to have an infinite amount of voltage in the resistance. Now, according to the conservation of energy, this has to be true, which means you would suddenly have to have an infinite voltage also in the capacitor. That doesn't make any sense because you're trying to discharge the capacitor and you would have to increase the voltage. It doesn't work. It's impossible. There's no way physically for us to have an infinite voltage across the resistance. So this is going to take a finite amount of time now. It won't have an infinite amount of current, but it will have a time by which all of the charges built up on the capacitor will discharge through the resistor to the other side. And the resistance makes sure that it takes some amount of time. If you increase the resistance, you actually increase the amount of time it takes to discharge. Okay, so if we do KCL here, we have two nodes. For the discharge circuit, what are our two KCL equations? Here we're not going to have an IS because we can't form a complete circuit with IS. So it will be IC is equal to IR. And then on 2, it's the reverse of that. IR is equal to IC. Because the current's coming from IR and going to C. Okay, but yes, Those would be our KCL equations. Okay, so this is what we have to work with. Now, this is true because the components are in parallel. This is true because the components are also in series. Okay, anytime you have components in series, the currents are equal. Anytime you have the components in parallel, the voltages are also equal. That does make the equation a little bit easier to solve than what we dealt with last time. So, let's just solve it. We'll go ahead and take this one. VC1 is equal to VR1. Now the problem is we need to get this in terms of only one unknown variable. We neither know VC1 nor VR1 at any time. Although we assume that it starts at VS, where we'll set VS as maybe equal to 10 volts. We'll say C is equal to 20 microfarads. And we'll say R is equal to 5,000 ohms. Okay, so we know this is true. How do we get this so that it's only in terms of VC? Oh, shoot, I forgot. This is equation set 1. This is equation set 2. Forgot to write out equation set 3. Does anybody know what equation set 3 is? It's for the components. Should be the same equation set as we dealt with for the last 2 examples in the last class.
VR equals IR times R.
Okay, that's 1. What's the other one? Yep, that's number 2. So we have VR equals IRR and IC equals C dVC dt. It's just the relationship between, hi Jenna.
Hi.
You gonna come sit in on this class again?
What class is it?
It's circuits.
Absolutely not.
Oh,
So sorry. Hey, you should check your email though.
I will.
For admissions email.
Okay, thank you. Okay, so here's where we're at. What do we do now? We started with a KVL equation. Now what? We're trying to derive our constitutive equation. What do we do? What is next? Well, if we're trying to solve for VC, we want to leave this alone, right? Which means we've got to change the other one. So how do we change this other one? What other equation do we have that has a VR in it? Yep, we can use the component equation and say VC1 equals IRR. Those two are equivalent because we have this fun equation right there. Now what? We know R, but we don't know IR. What equations do we have that use IR? IR equals IC. That is one of the KCL equations. So VC1 equals IC times R. What equations do we have that use IC? We go back to our component equation. VC1 is equal to C dVC dt times R. Now I'm going to take all of this and put it on so that we have our variables on the left side and then our constants on the right side. So what we end up with here is CR dVC dt plus VC is equal to 0. Now last time this was equal to VS. Why is this now equal to 0? It will, yeah. It's in equilibrium, this is headed to 0. This side of the function in our constitutive equation is known as the forcing function. Okay? A forcing function for any of these circuits is going to be your power supply, or it's going to be some function of your power supply. Here, when we flip that switch off, it's not connected to the power supply. So it's going to be driving towards 0 because there's nothing driving it at all. So this is our constitutive equation. Once we have our constitutive equation, the next step is to do what? So we drew the circuit, we got the equation sets, we derived the constitutive equation. What's next? Yeah, although we have to before we can find the time function, we need to assume the solution. But then yes, we find the time function. So we're going to assume the solution. VC is equal to VCC plus VCP. Okay? We'll assume that VCC has the form of A1e to the ST. And we'll assume that VCP has the form of A2. That's what we did last time. Because this is a first order system, this is a valid assumption. It changes next week when we talk about second order systems, and it will continue to change when we get back from project 1 and continue to talk about second order systems. Okay, so then Tal Caden said the next step is solve for S. Okay, and the way that you do that is by plugging in VCC into the homogeneous equation. In the homogeneous equation, you make the forcing function equal to 0, which it's already there. So here, this is CR dVC dt plus VC is equal to 0. We'll switch VC to VCC, so it becomes CR dVCC dt plus VCC equals 0. We'll plug in VCC, which is A1e to the ST. So CR d dt A1e to the ST plus A1e to the ST is equal to 0. what's the derivative of a1 e to the st?
So shouldn't in that formula one of the elements be negative?
Yes. Yes, it should. Which one do you want it to be negative? This one or this one? We'll make it. Sounds good. Thank you for pointing that out. That does change absolutely everything about this. Good catch. So what is the derivative of a1 e to the st? Hold on, I'm gonna put the s out front just for, because it, yeah. CR times s a1 e to the st minus a1 e to the st. Now, once again, we can divide out a1 e to the st, which leaves CRS minus 1 is equal to 0. Or S is equal to 1 over RC. That's interesting. Now, in order to make this work, actually in the end, this was supposed to be a positive. But the reason for that is because this here is supposed to be a negative. Because the current is flowing backward through the capacitor. Which means that we have to go back up here, change this, and that becomes a positive again. Because this is supposed to be a negative. So, good catch. I was just wrong on a different level. Okay, so S is equal to negative 1 over RC. Yay. Which, by the way, where have we seen this before? Huh? Yeah, it's a time constant, but where did we see this equation before? I've written this exact equation on the board last time. This is the same time constant as we had for just the RC circuit where things were in series. Well, these are in parallel, and this is a discharge circuit. Well, it turns out time constant has a pretty standardized form. If you only have one resistance and one capacitance, this is going to be your time constant. It has to be. It always is. Doesn't matter what the circuit looks like. Because it is degrading according to a certain amount of time, and the amount of time is dependent on both R and C. Units of R times C is actually equal to seconds. So 1 over RC is equal to 1 over seconds. Okay? We can calculate out S right now. What is R times C? What is R? So 5,000 times, what is C? 20 times 10 to the negative sixth. So that's going to be equal to negative 1 over 100 times 10 to the negative third, which is equal to a negative 10. Nice. Okay, so our tau value here is going to be equal to 0.1 seconds, because tau is equal to negative 1 over s. Okay, so we have tau is equal to 0.1 seconds. Nice. We're in a good place. All right. So we've solved for s. We know the value of tau, we know our time constant, we know how long this is going to take to discharge now. What's our next step? That's our last step. We got one more step to do before then. We have to solve for the particular solution. So this right here, we set our forcing function equal to 0 to turn it into the homogeneous equation. We are now going to leave the forcing function as is and solve for the particular solution. Okay, so now we do the non-homogeneous equation, and we plug in VCP. So CR dVC dt plus VC equals 0. We'll plug in VCP. What is VCP? It's A2. So we have CR d dt of A2 plus A2 is equal to 0. What's the derivative of A2? It's 0, so this function goes away. What we're left with is A2 equals 0. Now you will notice the way that we have this set up for pretty much every system, if you're solving for the voltage on the capacitor, A2 is going to be equal to the forcing function every time, unless the forcing function is non-constant. Okay? Here, because it's constant, this goes away, and we're left with whatever A2 is equal to the forcing function. That will happen every time. You will see that every time. So here A2 is equal to 0. Our particular solution is 0. And now we have to plug in our initial conditions. You were just a step ahead. Go back over here and erase this. As much fun as it was making you guys move and then working behind you. Okay, so our last step, to solve for A1, we need the initial conditions. At t equals 0, what is VC? Is it equal to 0? It is not. So what is it equal to? T equals 0, we flip the switch from on to off. It's not infinity because we don't have infinite volts, but it does follow this right here. At t equals 0, this relationship is still true, which means that our VC1 is equal to Vs. We could have a current of infinity as soon as we switch the flip the switch back, but our voltages are going to be Vs. We're not going to have an infinite amount of volts. So at t equals 0, Vc is equal to Vs. Why? Because Vs was charging Vc. Also because anytime you have the switch on, Vs and Vc have to be equal to each other. So t equals 0, Vc equals Vs, which is equal to 10 volts. Okay, so we'll go ahead and plug this back into what we know is our final solution. Vc equals Vcc plus Vcp. We'll plug in what we know for Vcc and Vcp, which are these two equations. Vc is equal to A1 e to the st plus A2. Now we know what the value of S is, we know what the value of A2 is, we know what Vc is at a certain time t, we can go ahead and solve for it. Okay, we know Vc is equal to Vs. And we do not know what A1 is, so I'll leave A1. We know S is equal to 0.1. So I'm going to go ahead and write this as negative t over tau, because st is equal to negative t over tau. We know what tau is. And then add 0 at the end for A2. So we end up with Vs is equal to A1 e to the negative 0 divided by tau. Then that's it. And this is only true at time 0, because at any other time, your Vc is not going to be Vs. So what is e to the negative 0 over 0.1? It's 1. So this turns into 1. What you end up with is Vs is equal to A1. And that's our final solution. Vc is equal to Vs e to the negative t over tau, where tau is equal to 0.1 second. That's the answer. Now this is a function that begins, if I plot it out, Vc begins at some level, Vs, and degrades to the final solution at 0. That's for discharge. If you'll remember, when this is charging, according to the way this circuit is drawn, it looks just like this. And that's charging. That's flipping the switch on. It instantly charges because there's no resistance between the battery and the capacitor. You can create a loop that does not have a resistance in it. So that's discharging a capacitor. Okay? Discharging a capacitor. Let's look at steady state solution here. What is the steady state solution for the voltage across the capacitor when it's discharging? It's 0. You actually, I know your name and I can never remember it when I'm in class. What is your name? Ben?
Yeah.
Okay. Yeah, because I look it up outside of class because I'm like, God, I forgot his name. And then I come home to class and it's just gone again. You were actually right when you mentioned that when we solved for A2, what we were solving for was the steady state solution. Here, when you're solving for the non-homogeneous equation, this particular solution, what you're actually solving for is the steady state solution. Okay? Here, this is headed to steady state. And our A2 is telling you what it's going to do in the long run. Why? Because this is not dependent on time at all. For a DC system, A2 will not be dependent on time. For an AC system, A2 will be dependent on time, but it's going to be a function of your input voltage. This is the steady state solution for the system. What this is here is what's known as the transient solution. This is a time-dependent function that goes away. Okay? This here goes away. It experiences constant decay, which is why it's called a transient solution. Okay? So, complementary solution is your transient, which means it just changes. It's the time-dependent change that happens once. And your particular solution is your steady state. And this is true for every system. This isn't just true for this one. If we know what the complementary solution is, we know how it's going to transition from wherever it was to wherever it's going to be. Now, if this system had started at VC equals 0, there would be no transient solution, because this here would have been A1 equals 0. If it starts at its steady state, A1 is going to be equal to 0. It has to be that way because there's no transient. There's no change. It doesn't have to adjust from the system behaving one way to the system behaving another way. It already is there. It's already at steady state. So that's interesting to note. Another interesting thing to note here. Last week I told you that at steady state, capacitors behave like open circuits. That's still true for a DC circuit. Which means in this circuit, because we have a DC voltage source, our capacitor is going to behave like an open circuit. If you have a circuit that just looks like this, you're clearly not going to have any current passing through that resistor. You have no current flowing through the system, and quite frankly, the voltage across those two ends are equal to 0 because you don't have any current flowing through this resistor. You can't have a voltage across the resistor if there's no current. So that tells you everything you need to know about the end solution. In steady state, there's not going to be any voltage, and there's not going to be any current. In a charging system, there is going to be a voltage at the end. Okay, if we plug this into a battery, at steady state, there is a voltage between those terminals. But because it's detached from the battery, because we depress the switch, there's no voltage, and there's no current either. All right, let's go ahead and take a 10-minute break. I'll see all of you back